Hello students, I am Vishwajit Nath. Welcome to my YouTube channel Best Physics Guide by Vishwajit Nath. Today I am going to discuss about LED or light emitting diode. This is the circuit diagram of light emitting diode. Here this diode is connected in forward bias with the external electric cell. This is the load resistance RL and this is the electric cell. The positive pole of the electric cell is connected with p-type and negative pole of the electric cell is connected with n-type of the diode. When the energy gap between the high energy level and the lower energy level is minimum 1.8 electrovolt, then we get light from this diode. When current passes through this diode, then the free electrons at the high energy level jumps to the holes at the lower energy level. That is, the electrons at the high energy level jumps to the holes at the free holes at the lower energy levels. Okay. In this way, this electron radiates or emits some energy. This energy we get as a light energy or light radiation. If nu be the frequency of the emitted light, then H into nu is equal to capital Eg. Here capital Eg is the energy gap between the high energy level and lower energy level. Here nu H is the Planck constant. When current passes through this circuit, then the free electrons first gain some energy and jumps to the high energy level. After that, these free electrons can jump to the high energy level to lower energy level. Then it emits some energy. This energy we get as light energy. That's why this is known as LED or light emitting diode. To get light, the minimum energy gap between high energy level and lower energy level is 1.8 electrovolt. This is the graph between potential difference and current. This is the graph of forward bias. This graph shows the variation of current with potential difference for red light. This is for yellow, this is for green, and this is for blue light. Since the minimum energy of the photon particles of visible spectrum is from 1.8 electrovolt to 3 electrovolt, 1.8 electrovolt to 3 electrovolt. That's why the minimum energy gap must be 1.8 electrovolt or greater than 1.8 electrovolt. Therefore, we cannot use silicon, germanium or germanium as the LED, or we cannot use silicon germanium to make LED. We use gallium arsenide phosphide to make LED. For X is equal to 0.4, we get red light. For X equal to 0.65, we get orange light. For 0.85, we get yellow, and for 1, we get green color. And we use silicon, germanium, or GaAs, that is gallium arsenide, to make infrared LED. Since the energy gap of silicon, germanium, or gallium arsenide has less than 1.8 electrovolt. Next, photodiode. In a photodiode, when light incident on the diode, then electricity produces. This is known as photodiode. This is the circuit diagram of photodiode. Here, photodiode is connected in reverse bias with the circuit. That is, P is connected with negative pole of the electric cell, and N type is connected with the positive pole of the electric cell. When light incident on the diode, then absorbing the photon energy or light energy, free electrons and free holes are produced. Free electrons and free holes are produced. Due to the diffusion, at first they move towards the depletion region, but after that they move to the away from the depletion region. Here the free holes moves from the p-type, free holes move to the p-type, and free electrons move to the n-type. That is, inside the p-type region, the free holes move to the p-type, and inside the n-type, the free electrons move to the n-type. That's why in the reverse bias circuit, this free holes produces current. This current produces by the minor current carrying conductors, or minor current carriers. Therefore, we get the reverse bias voltage. This is the diagram, or this is the graph between V and I in the reverse bias voltage. In this way, we get the current by light. That's why it is known as photodiode. In this case, the light is directly proportional to the intensity of the current is directly proportional to the intensity of incident light ray. In this case, the current of the circuit is directly proportional to the intensity of incident light ray. Here, energy of incident photon must be greater than the energy gap. That is, h nu greater than Eg. Here, nu is the frequency of the incident light, and h is the Planck constant. Solar cell works like photodiode, but in this case, no external cell is connected. It works with photovoltaic process. Here, the energy of incident photon rays is greater than Eg, that is energy gap between the conduction band and the valence band. When the incident photon, the photon falls on the diode, then electrons and holes are created. More free holes and free electrons are created. Due to the diffusion, at first they move towards the depletion region. Then they repelled, and repelled by the potential or electric field in the depletion region, and then the free holes in the p-type junction moves towards the p-type layer, and the free electrons inside the n-type junction moves towards the n-type region. In this way, the current produces, in this case, the light energy produces current or electric energy. Here Eg or Eg must be, value of Eg must be 1.5 less than 1.5 electrovolt. That is, energy gap between valence band and the conduction band must be less than 1.5 electrovolt. That's why we can use silicon to silicon or CuInAc2 for using the solar cell. Eg or the energy gap for silicon is 1.1 electrovolt, and for CuInAc2 is 1.04 electrovolt. This graph shows the variation of potential difference with current. Okay. Here VOC is the open circuit voltage and ISC is the short circuit current. This graph shows the variation with the potential difference and the current. Next, Zener diode. In my previous video, I already discussed about Zener effect. You know that when the diode is connected in reverse bias, then when the reverse potential difference increases, but the reverse current do not increases sufficiently. But at the some value of the reverse bias, the reverse current suddenly increases. This potential difference or this potential is known as Zener voltage. This voltage is known as, in the reverse circuit, is known as Zener voltage, and this effect is known as Zener effect. And this is the symbol of Zener diode. Zener diode works during in the breakdown voltage, Zener breakdown voltage, and Zener diode always connected in reverse bias with the circuit, since it works according to the Zener effect, and we know that Zener effect only occurs when the circuit is in reverse bias. And Zener diode is highly doped. Zener diode is highly doped. When the variation of the reverse potential is very small, although the variation of reverse potential is very small, but the current can pass through the diode in the Zener voltage or Zener breakdown voltage is huge. That is, although the reverse current passes through the Zener diode in the Zener breakdown voltage is huge, but the variation of potential difference between the Zener diode is very small. This property is used to regulate voltage. That is, Zener diode is used as a voltage regulator. This is the circuit diagram of voltage. This is the circuit diagram that it shows how we use a Zener diode as a voltage regulator. This is the input voltage of the electric cell. This is the input voltage of the electric cell. R is a resistance, and main current I passes through R. This is the load resistance RL, and current passes through the load resistor. Resistance is IL, and the Zener diode is connected parallelly with the load in the reverse bias. IZ is the current passes through the Zener diode. Here I is equal to IZ plus IL, and VZ is equal to, that is the potential difference across the Zener Zener diode, is VZ is equal to V minus IR, And since Zener diode and load are connected parallel to each other, therefore the potential difference across load line or load resistance is equal to also Vz. This equal to IL into RL. When the current I increases, then maximum current passes through the IZ, but the value of Vz remains constant. When the current decreases, then IZ also decreases, but the value of Vz remains almost constant. That's why the potential difference across RL always remain constant. When the either V increases or decreases. Okay, that is when V increases, then the value input current I also increases, but maximum current passes through IZ, and the potential difference across the RL, that is Vz, remains constant. And when V decreases, then the value of I also decreases, but the value of I also decreases and IZ also decreases, but the value of Vz remains constant. That's why the potential difference across RL remains constant. In this way, we can use Zener diode as a voltage regulator. Today, I am going to complete my discussion. I hope you understand. You can understand these topics, and please subscribe my channel. Have a nice day, and thank you for watching my video.